you can think of it in terms of fundamental resonance matching in the complexification of the system, so that you have emergent properties that are the result of a set of variables and set of specific system having increase in complexity as a result of interaction in the system. So you can see, for instance, from the Planck field, right? You have high level of complexity. So you have 10 to the 60th Planck that makes up one proton, right? But at one proton level, you have still a reduction to 10 to the 40th, which is huge reduction in terms of information exchange between the system, right? So this 10 to the 20th entropy across the system, right, is going to create a very a set of variables, right? That's gonna, so you're gonna have an entropic, like a dampening effect across the scales, across values, and so but since the system is unified, meaning the system is connected at all scales, there is, although you have dampening across scale, you have nonlinear interaction between points, meaning that the system is warped in each point, so it's entangled, right? So it's instantaneous. So so the complexity increase, right, in like the chaotic function of the fractal, if you'd like, as the feedback information loop, the dampening across the feedback information loop from one scale to the other increase, right? So that's why you get, huge amount of, if I'm not answering your question directly, you tell me, but I think I am, meaning that as you get to like larger structures, like biological systems, chemistry, and these, at this level, at these scales, the entropy, the dampening across the feedback is producing complexity, right? Because there's more, angle of freedom, if you'd like, in the information network. So that makes, you see what I mean? So you see, for instance, the fractal structure at the biological scale has a resolution that's fairly wide, meaning it can vary largely, right? And you can get like chemical bounds that like vary widely and get different molecules, right? Because you have more vectors of freedom in the geometry. But when you reduce closer, where the dampening is not so high between the Planck field and the proton, then then you get high level of accuracy, less complexity in terms of complex relationship, complex systems. Do you see? So you have very, very standardized, if you'd like, variables. The variables are reduced. You have less freedom, right? You get higher freedom on the larger scale, and that's how more complex systems emerge. So for instance, you can think of the entropy of the brain, right? Or let's just say you could think of the energy level of a system, right? And when I mean energy, I'm talking about the emergent property of the Planck field, right? So to be clear, right? It's an emergent, it's a secondary effect of the dynamic of space, right? And so that emergent property increase in entropy, right? Increase in energy and complexity, right? As you move away from the Planck field in scale. In the feedback, you have a feedback and a feed forward, right? So you have one, yeah. So you have one that's entropic in nature, and then you have one that's negentropic in nature. You see? Yeah. So you have a function in which you're increasing complexity, and then you have a function where you're decreasing complexity. And so that and the two are feeding back onto each other, right? But it's a little more complex than that. That is that when you have the negentropic part going back to singularity, going back to simplicity, right? You're actually going back to unification, to oneness, so that actually the complexity is across all nodes. So you could actually almost reverse it and think of it as all nodes complexity being the simple, because it's unified, right? But it doesn't mean it's not complex.